All right, let's get started. So in the last lecture, we looked at how we can look at the noise levels and then try to infer something about the statistics. But I think, as you would have seen, it's not a very simple technique. There's a lot of complications. We have too many electronic units involved, and then we have to be extremely careful. So one of the more popular ways of looking at light is by using correlations. So statistics is one, we have looked at that. Today we will look at another phenomena which is known as correlations basically, and to actually look at light based on the correlations, we'll have to understand the concept of coherence. We'll do that, and then I'll also introduce the idea of a second order correlation function G2, and then we will stop that for this week. In the next week, I'll really talk about how the second order correlation can give you information about the type of light, whether it is quantum light, classical light, and so on, okay, or coherent light, and subpoisonian or superpoisonian. We'll look at that, okay. So before we go into that, let's first look at coherence. So if you have a perfectly monochromatic wave, a coherent, which is extending in over infinite time, then you have a situation like this in the top, which is basically a coherent sine wave, right? So there are no disturbances. It's a coherent sine wave. What do I mean by that? Well, if I know the amplitude and phase at a particular point of time, let's say, given f of r comma t, let's say, okay, at one particular time, r comma t, if I know, at any other point of time, I can calculate the amplitude and phase, okay. So given this, we can calculate f at any other r and t. Okay, this is the idea of a coherent wave. Okay, that means there's a fixed relation between the different points on a wave in space and time. Schematically, you can think of it like this: a wave which is traveling in time, and then in space it is perfectly, there are no disturbances. But this is a very, it's an idealistic situation. You'll never have this in reality. In real life, many times, you have incoherent sources or partially coherent sources. So to categorize those things, we define two terms: the temporal coherence and spatial coherence. Okay. So first, let's say, I'll talk about the temporal coherence. So instead of a perfect source, you will have a finite temporal coherence. What does it mean if you have a temporal coherence? Suppose if you given, let's say at a time t1, f of r, at t1 the wave, you can estimate time, the wave, okay. We can calculate, sorry, f of r at a t2 provided t1 minus t2 is less than tau c, which I'll call as coherent time. So what I mean by this is, let's say if you take one point here on this wave here, I can estimate at a different point t2 provided the time is less than the coherent time. That means within that coherent time there is a fixed phase relationship that exists between different parts of the wave, but then there's a discontinuity here, the phase jumps, right? These are phase jumps. So these phase jumps will make it impossible for us to predict what is a long term, if over a very large time, let's say time is greater than coherence time, twice, thrice coherent time, then it becomes impossible for us to know what is the amplitude and phase of the wave. Okay, if it's just a phase jump, then the amplitude will remain same, but then there is a discontinuity. But you can also have, sometimes amplitude changes as well. Okay, so in this case, the temporal coherence is basically a measure of for how long the wave is coherent. In this case, the wave is coherent here for this duration. Again, there's a phase jump, but again coherent for some time, and so on. Okay, this is coherence, spatial coherence, temporal coherence. The other thing we'll have to look at is spatial coherence. The third thing is finite spatial coherence. In this case, if I am given a wave which is at a particular time, given f of t comma r1, at a particular point I know this wave, then we can calculate at a time can calculate f of at the same time but a different point R2, provided R1 minus R2 is less than coherence length. So I can define something called as a coherence length. So in this third picture here, if I have a particular point here, I can calculate at any point of time at a different point R2, provided the distance is less than coherence length. That means if I cross that, if I go very far away from the source or the point where which I make the first measurement, then I cannot know. There is no fixed relation between them. That is the idea of spatial coherence. Okay, and these are internally linked. They are not completely different because a wave is propagating in both space and time, right? So they are linked. And if you have very good temporal coherence, it manifests as the line width. The temporal coherence manifests as the line width of a laser. For example, if you take helium neon laser, we say that the line width is few kilohertz. That means it has very, very long coherence time. Whereas if you take, let's say, the white light, it has many different wavelengths. So effectively, you don't really have large coherence time. So the bandwidth is very large. Okay, it has a short coherence time, so bandwidth is very large. Similarly, spatial coherence is basically if you have a wave which is coming from one particular source, you will have one single point source, let's say, then it will be spatially coherent. But the moment you move away from that source slightly far away, then the coherence is lost because you have addition of two different waves and then they will constructively or destructively interfere. In fact, this idea was coherence was central in the astronomy. They were trying to look at the sizes of the stars. So you ever wonder, like, if you look at the night sky, you have these stars, and people were trying to actually calculate the diameter of those stars. How big are the stars? And the way they were doing with that was using, what are known as interferometers. So you take light, you put a big interferometer wherein you have two detectors spaced apart, and then you look at how the correlations exist. If you put two mirrors, and then you make the light interfere, and then you look at the fringes. If the two light sources or two mirrors which are collecting the light from a very distant star are actually creating constructive interference, you can look at the visibility of those fringes, and if as you move the position of the mirrors closer or farther, the visibility will change. Based on that, you can actually calculate how much is the spatial coherence of the source. That means I can understand how big is my diameter of the star. So these experiments were done in the 20s and 30s and so on. Initially Michelson did it, then there were variations that were done, and it is very central to the idea of astronomy, in determination of sizes in astronomy. So one example is again here. So if this is a simulation that was done to look at what happens when you have, let's say in this case, fringes as a function of both position and time. So in the y-axis you have the position. So you'll see that in the central region, in the region here, you have very good fringes. That means the bright and dark spots are clear. That is because you have good coherence there. But then if you go to other places, the visibility is very low, indicating that there is no coherence there. And then if you have different times as well, this is more complex. I mean, the details of simulation are not really necessary for us. Just to emphasize the point that if you have coherence, you have good fringes. That is the reason why whenever, if any of you did the experiment on Michelson interferometer, it's very, very difficult to do it with a normal lamp. With a laser, you put it there and then you get fringes. That's not very difficult. But remember, Michelson did the experiments in late 1880s, wherein there was just lamp. And then to actually see these fringes was hard. I mean, you have to make a very finite aperture. You have to find a sodium lamp, which is very, very sharp. So it was not easy to do it. Okay. So nowadays, we put a laser in the lab and then we get interference fringes within 5 minutes. So that's not that simple. Okay. So the idea of coherence is very, very important in this scenario. And now in our context of this course, it is important because there is a very, very famous experiment or very famous interferometer which is called as Hanbury Brown-Twiss. Hanbury Brown, I think, was one person and Twiss is a second person. Okay. So basically they did this interferometer. They looked at the Michelson interferometer and they tried to improve it. They suggested a scheme because if you're having lenses, the lenses are basically very difficult to move around, and then there are issues with that when you look at fringes. Calculating the visibility of fringes is not a very simple thing to do. So what Hanbury Brown-Twiss they proposed, so in short, we can call them as HBT. That is a popular terminology. So what they proposed was, instead of actually using lenses and then trying to make beams interfere, take two lenses, which are, take two lenses, and then you focus that light onto two different photodetectors. So the experiment here was, you take one, let's say, beam splitter, you have the light which is coming from a source, and then you have transmission and reflection. And so you make the transmitted light go on one detector and the reflected light go on one detector. And then you take the detector and look at, pass it through an amplifier. Okay, a low, basically capacitively coupled amplifier, so that you only have the AC signal, not the DC signal. Okay, so when you have such a scenario, you have two of these things which are combined, and then you get basically the product. Okay, so if you, let's assume you have an intensity initially, let me call this as I1, which is intensity incident on the first photodetector, and that I'll give it as the time variation I would assume is basically the mean value of I1 plus some fluctuations in I1, delta I1 of t. Okay, so now when you have that sort of an intensity which is incident on the detector, okay, what is the current that will generate? It will generate a photocurrent. We have seen that. And so this photocurrent now, when you have AC coupled amplifier here, this generates delta I, this is I2, sorry, in this case I2 here, that other one is I1. So delta I2, which is proportional to, the fluctuations in intensity, right, of I2, proportional to fluctuations in I2. What are the fluctuations in I2? Delta I2 of t, right? The average value, the DC value, will be blocked by the capacitor, and you essentially have only AC that's coming in. Similarly, you have the same thing here. You will have delta I1, okay, and then you take a product of it. So the output of the Hanbury Brown interferometer, HBT interferometer, IHBT, is going to be proportional to, basically there are two things, right? The fluctuations in the source I1, okay, and one additional I1 of t, the fluctuations in source I1, and they also introduced a delay here. In the I2, they introduce an electronic delay. Okay, I mean in the original version it was actually in space, but then nowadays we actually do temporal. Instead of changing the position of it, we change the time. So in the modern form, this is basically delta I2 of t plus tau. You have fluctuations in time. Okay, so at T1 you have the direct beam, and then you second beam you delay it by a certain amount tau. So you're writing that. So basically the output of it is going to be proportional to both fluctuations in the average value of the product of fluctuations in 1 and the delayed version of 2. Okay, so now let's see what happens. Okay, so if you have, let's say, a scenario wherein I have my I1 of t, which is the intensity incident on the first detector, that is equal to I2 of t. So I have the same intensity that is incident, and then I'll call it as I of t. Okay, essentially you have a 50-50 beam splitter. If you have a 50-50 beam splitter, you have this scenario, and this intensity that basically is going to have some average value I, and then there is going to be some fluctuation delta I. Sorry, not average value of fluctuation. Should be delta I of t. Okay, so now this is the incident intensity, and that is same for both detectors. So in such a scenario, let's say if tau is 0, the delay is 0, what do we expect the output of the HBT to be? IHBT now is going to be proportional to delta I of t into delta I of t. So delta I of t square. Okay, when tau is 0, basically. What will this be? Will this be 0? Delta I of t square, will it be 0? Okay, so if you look at the noise, right, we assume that it's a random noise. So there is some level intensity and there is some fluctuations around that. If you take the time average, the angular brackets represent the time average. So if you look at a simple intensity profile, you will see that the mean value and then the intensity on an average should be 0, because it's going to be above and below that equally. There's a random probability, and then the overall average should be 0. But if you do an I square, it's not going to be 0. It's going to be something not equal to, it's greater than 1, right? It's I square. So this is greater than 1 for tau equal to 0. Similarly, if tau is much larger than tau c. Okay. So now basically your I, current through the HBT is proportional to delta I of t, delta I of t into delta I of t plus tau. So what will be the time average now for tau much greater than tau c? The question is, what happens when you have the delay much larger than the coherence time? There is no correlation between the fluctuations. At the input 1 and input 2, the fluctuations will be completely different. There is no fixed relation. That is why if you take a product of it and take a time average, you are going to end up with 0. Alright. So in this case, the output is going to be 0 for times greater than coherence time. So now, by changing the delay, I have a way by which I can figure out how much is the coherence time of my source. Okay. And if I, let's say in the original I said Hanbury Brown experiment, they simply made this one of the detectors as movable so that they can move it. Once they move it, again, after a coherence length tau LC, I will not have any coherence. So if I measure the same thing, current, as a function of distance also, I'll get coherence length over which my coherence is there. In this case, it's schematically shown as a mirror here, but yeah, from different positions in the mirror, right? So initially you have this transmission anyway, but the moment you move it, you're getting light from a different position, right, in the source. So that spatial coherence can be mapped by moving the detector. Okay, but in general, it turns out that the time is much more simpler for us to do experimentally. Okay, that's why in modern form, most of the time we just do G2 in time. We change the delay. All right. So once you have such a scenario, what we can do is, we can actually, in the quantum optics community, there is a very common term that is, common function that is used, that is called as second order correlation function, G2 we call it. Okay. So G2 is simply the time average of product of intensities. So you have the initial intensity and the delayed intensity. So it's a correlation, product of it, and then taken time average, and then divided by the time average of the first and the second intensities. So you have two of these beams. One beam is delayed with respect to the other. You take a correlation, and then this is a second order correlation because we are actually taking intensity correlation, not electric field correlation. If you take field correlations, that becomes the first order correlation function. Okay. So now we have seen that I of t is going to be equal to the mean value of I plus delta of I as a function of time. There is some correlation. And I also said that if you take the time average of delta of I of t, that is going to be equal to 0 because it's random fluctuations. Now, to determine what is the second order correlation function, it's essentially the same as what we have seen before, but let's go through the motions. So if you look at the numerator is going to be, if you calculate it for basically delta I of t, not delta, I of t, right? The I of t, time average of it for tau much greater than tau c. If you have this scenario, what will happen? So each of this, you can substitute. So this is going to be time average of average intensity plus delta I of t into average intensity times average intensity plus delta I of t plus tau. This is my product, and then whole thing time average. So I can expand this. So if I expand this, I get basically time average of I square plus delta I of t time average into I plus I into delta I of t plus tau time average plus delta I of t into delta of I of t plus tau. time averages. So this is what you get output. What does it mean? So now we know that we have already seen that if you take a time average of I of t, that is going to be 0. So these terms will go to 0. All of these terms go to 0. So you are left with I square, average intensity square. Okay. And so now G2 of tau, G2 at tau equal to tau much greater than tau c is going to be equal to I square by I square, average I square divided by average I square, that is going to be 1. Okay. But if you do the same thing at tau equal to 0, okay, so if I calculate, this is, sorry, it's greater than, in this case it's going to be 1, and if I do G2 at tau equal to 0, so now since my tau is equal to 0, the numerator is going to be I of t into I of t divided by I of t average whole square. Okay, this is going to be my G2 of tau equal to 0, Now let's try to look at what happens to the second order correlation function as a function of delay. Okay, so to do that, I'll plot the x-axis tau, on the y-axis G2. If I do that, and let's say we have already seen that if you have a coherent wave, okay, what will happen? A perfectly coherent wave, then the intensities are basically, there are no fluctuations, right? And so I of t, in the case of a coherent wave, for a coherent wave, G2 of 0 is going to be simply I, even if, yeah, average square divided by, sorry, this is going to be I square divided by I of average of I whole square. So this is for a coherent wave, it's going to be equal. So you'll end up with G2 of 1 all through. Okay, this is going to be G2 equal to 1. That means anyway at large coherence times we have, at tau larger than the coherence time we have 1. But even when tau is less than that, tau equal to 0 also, you still have basically G2 of 1. But if you have a random fluctuating source like a thermal source, for time greater than coherence time you get G2 of 1. But what happens at time equal to 0? Well, now you have basically, there are fluctuations here when time is basically less than, when G2 is 0, G2 of 0, you'll have fluctuations, and that fluctuations are getting squared. And then because of that, the G2 of 0 is going to be greater than 1, and you end up with a scenario like this. Okay. When you have a source which is a chaotic source or a thermal source, this is for a thermal source. Okay. And this is for a coherent source. So you get what we are saying here, right? So when we are talking about I of t and time is 0, right? When time is 0, you're taking a product of I, right? Now there are fluctuations. The fluctuations are getting squared, right? Average value is there. The fluctuation is getting squared. If the fluctuation gets squared, what happens? It will never go to 0, right? If you have a chaotic source, the delta of IT, right? Delta I of t into delta I of t. So that is going to be definitely larger than the average value. You see that? Right? So that's why if you have a coherent source, then exactly identical, right? And then you have 1. All right? Coherent source, I mean, there's no intensity fluctuations, right? So you get I square, mean value is equal to that. Okay. So let's just take one example. So I just wanted to introduce this concept of a correlation function, and then we will actually next week we'll go into further details about this coherence function. Okay. So now just a simple example of, let's calculate G2 of 0, so second order correlation function at 0 for this particular intensity, which is varying as a sine wave. So we know that the correlation function, second order correlation G2 of 0 is going to be equal to I of t into, again, I of t, right? I of t square essentially divided by average of I square. So what is the numerator? Now my numerator is going to be this function. So I naught is a constant, so I'll take it out, and then time average of 1 plus a sine omega t, correct, squared, time average of that divided by average of the I of t is basically I naught. Okay, so I naught will go off. And what is my time average of the numerator? In the numerator, these things will cancel out. My time average is going to be equal to 1 plus a square sine square omega t plus 2a sine omega t. This is the time average in the numerator, right? So now if you look at this, so time average of sine omega t is going to go to 0. Basically I can take it out as 1 plus time average of, so there's an a square, and then time average of 1 plus 2 cos omega t, 1 minus cos is 1 minus cos omega t by 2, right? So again the second term will go to 0, so that should be equal to 1 plus a square by 2. All right, if you have this, so my G2 of 0 now is going to be 1 plus a square by 2. So it is not 1. Okay. All right. If you have sine omega t, what happens? If I of t is simply a sine omega t, there is no 1 plus. Well, 0 by 0. Right? Time average of the top, I mean I naught actually, not, I naught, right? I naught is average. Well, sine omega t will average, time average is going to be 0, so 0 by 0. Okay. So, any questions? What is G2 square? No, G2 of 0. Well, what is G2 of 0 equal to 0? Well, we'll talk about it next week. Right now, it cannot go to 0. It will be 1 or greater than 1, so far what we have seen. So in the next week, we'll actually talk about what are the implications. We'll consider different types of sources and we'll try to see what happens, how the correlation function behaves. So for now, I just wanted to introduce this idea of a second order correlation function, that's all. Which is simply, if you are given an intensity, it is product of that in the numerator, and then they divide by the time averages of the individual intensities. That's a second order correlation function. Okay. So we will discuss more about what this means and so on in the next week lecture. All right. Okay. So so basically what did we do in this week? We introduced the idea of statistics. How the different types of sources can be classified based on the statistics, Poissonian, superpoissonian, subpoissonian, and then how do we detect it? Okay. If you need to have low intensities if you want to detect them. If that is not available, then the only option is to try to look at noise. That is also not very comfortable or convenient. So then we introduced the idea of correlations based on the idea of coherence in light. We have introduced this correlation function G2, and that is a very popular way of looking at the quantum nature of light. So we will discuss the details in the next week. All right. So with that, thank you so much. We'll stop here.